Well, in this recording, I wish to talk about some more examples of the curve sketching. And of course, we still have the guideline. Okay, so let's look at another example. Example number 2. This example, I pick from the textbook. Okay, the function is f of x equals to, and here's the function. We got x squared on the top, and the denominator is square root of x plus 1. And we're going to go by the guideline. There we go. Domain. Determine the domain. We need to guarantee the denominator is not 0. And we also need to guarantee when we take a square root, the number take square root must not be negative. So these two combined, x plus 1 has to be larger than 0. As a result, when we solve this inequality, x will have to be greater than -1. So the domain would be x is greater than -1, or you can say x has to be from the interval of from -1 to positive infinity. There, intercepts. And the easiest to find is the y-intercept. So we're going to substitute, we're going to set the input equal to 0, x equals 0, so we get 0 squared in the numerator. And in this case, the the y-intercept is 0, 0. It's a point. And to find x-intercept, we're going to set the function equal to 0. We set y equals 0. When we set the output equal to 0, we got x equals to 0. Because if x squared is 0, x is 0, right? So we get x, the numerator must be 0. As a result, x equals to 0. So x-intercept and y-intercept happen to be the same point. Okay, we only have one x-intercept, and that is 0, 0. X-intercept. Oh. Put it right here. Okay. So we found both x-intercept, y-intercept, and symmetry. Symmetry. Obviously, this is neither even nor odd. There's no symmetry. About y-axis. Okay. And there's no symmetry about x-axis, about the origin either. So you can just simply check if it's an even odd function, and it is neither even nor odd. Asymptotes. Okay, asymptotes. Asymptotes, what most likely to happen is that we look at the denominator. Okay, when x is approaching -1, okay, x can only approach -1 from larger than -1. Okay, because -1 is not included domain, but -1 is right outside the domain. So we would consider, when we consider the vertical asymptote, we will be looking at, okay, we're going to put the horizontal asymptote under. Okay, we're going to come back to it later. Just in it a little bit, right? So when we approach -1 from larger than -1, we're going to observe, and we're not going to approach -1 from smaller, right? So these are not going to be relevant. And the function we have here is this piece. Okay, so we're observing this function right here, right? So we observe this limit, which is right here. Okay, I should put a little parentheses about -1 to make it clearer. Okay, when this happens, you can see when x is approaching -1 from larger than -1, the numerator is approaching 1, the denominator is approaching 0. So that's going to be a positive infinity. So we have a vertical asymptote. Okay, so the vertical asymptote, which is 1, which is going to be x equals to -1. Horizontal asymptote, because the domain is from -1 to infinity, so we're not going to approach the negative infinity. So we can only look at the limit of the function when x is approaching positive infinity. So when we look at the function as x is approaching positive infinity, the function we're looking at is this piece, right? And we would like to find the limit. We would like to find the limit. And what do we find? As x approaching infinity, okay, as x approaching infinity, what we get is that we have the top approaching infinity, the bottom approaches infinity. We can actually use L'Hopital rule. Okay, we can apply L'Hopital rule. The derivative of the top is 2x. The derivative of the denominator is 2 times 1. Wait. 2 should be in the bottom. 2 times square root of x plus square root of x plus 1 under 1. Okay, using chain rule. And then as a result of this, if we simplify this complex fraction and we multiply both top and bottom by this piece, so we're gonna get just 2x multiply that. Right? So that's a 4x. That's a 4x. And that's going to be positive infinity. That's going to be positive infinity. Okay. And in this case, we don't have a horizontal asymptote. Okay. We have no horizontal asymptote because of the following reason. Okay, it doesn't approach a finite number. All right, so all of these, A, B, C, D, those are the things we could have done, without the knowledge of calculus. And let's look at the interval of increasing, decreasing. So finally, we get to take a derivative of the given function to identify critical values, right? So if f of x is such, what's the derivative of it? Apparently, we're going to apply quotient rule. Okay, applying quotient rule, we're going to, the denominator will be squared. And the derivative of the numerator, which is 2x, multiply square root of, x plus 1, minus x squared stay the same, and multiply the derivative of the root of square root of x, and that should be equals to 1 over 2 times square root of x. The derivative of x plus 1, of course, is 1. So we got that expression. Okay, so let me open the door, so kind of hot. All right, so let's simplify this expression. How do we simplify this expression? Okay, we obviously have a complex fraction here. And we just use our technique of multiplying the common denominator. And what is the common denominator here? The common denominator here is 2 times square root of x plus 1, right? So we're going to multiply that on the top, which is going to be on every term, right? So let me show you. Be patient. You have your paper pencil with you. So we're going to multiply the common denominator on both top and bottom, which is 2 times square root of x plus 1, and divided by the same quantity. And this is principle number 1 is being honored. And then the top is going to multiply. The numerator has 2 terms, right? Distribute it. And the denominator will multiply with the denominator. So this piece is used, right? And then we simplify. When we simplify, you can see this piece, that's going to be 2 times 2x, that's going to be 4x, right? That's going to be 4x. And the root x plus 1 times root x plus 1, that's going to be x plus 1. And this piece, we're going to have a reduction, right? So we only have x squared left. Denominator, you can just organize it a little bit, and you can put the 2 in front of it. And this is root x plus 1 squared, and this piece is just x plus 1, right? So if you like to write it that way, it's x plus 1, right? Now we are closer to a factored form. We are closer to a factored form. And in this form, we have 4x times x, so the 4x squared, right? And 4x times x, 4x times 1, that's going to be 4x. And minus a x squared, so that's altogether is going to make it 3x squared plus 4x. We can do a little factoring because we prefer the factor form, right? So if we factor this, we will get, we factored out the x, right? X is out, and one of this x is out, so x is here. So finally, we have the first order derivative in the factored form. Once we have this factored form, okay, be aware, right? The domain is going to be, still is going to be x larger than -1, right? That's domain. So we're going to look for, because we're trying to figure out the intervals of increasing, decreasing, right? So we like to know the sign of the first order derivative. What are the signs? And this piece is going to be positive. How about x plus 1? X plus 1 is going to be positive because x is always greater than -1, right? X is always greater than -1. So x plus 1 is always positive. So the denominator is always positive. The question is, how about the numerator? Numerator x may change sign. So when you look at the number line, so when we look at the number line, we're gonna study the sign change, right? So we study the sign of x. Okay, it's just so much easier just to write it out. Okay, And have a little picture sometimes helps, right? So starting from -1, right? And of course, we have a 0 here, right? So x between -1 and 0, that's going to be negative. At 0, of course, is going to be 0, right? If x is larger than 0, it's going to be positive. How about 3x plus 4? How about the sign of 3x plus 4? 3x plus 4, right? The sign of 3x plus 4, well, when does it, you could think of, well, 3x, when does 3x plus 4 equal to 0, right? From that, so you can do just a little bit analysis, right? You do a little analysis. If 3x plus 4 is 0, what does x equals to? Right? X will be equal to negative 4/3. Negative 4/3. Well, x is larger than -1. Where's negative 4/3? Negative 4/3 is smaller than -1. Right? So 3x plus 4 will never be 0. Right? 3x plus 4 will never be 0. If you plug in any number on 3x plus 4, which is for x is larger than -1, so what will happen? Let's give it a try, right? If x is larger than -1, what happened to 3x plus 4? 3x plus 4. If I substitute x by -1, so 3 times -1 plus 4 equals to 1, and that's going to be positive. What does this mean? For any x is larger than -1, 3x plus 4 is always positive. Okay, do we see that? What does that tell us? What does this tell us? What does this tell us? 3x plus 4. If you plug in any number in the domain of f, you plug in negative 0.9, okay? You plug in any number between -1 and 0, it's going to be positive. If you plug in a positive number, it's going to be positive. So 3x plus 4 is always positive, right? So this is a positive, and so this doesn't change sign. What you see here is that only thing that makes the sign change is x. Okay, so this is a positive. So the only thing that changes sign is x. When does x change sign? When x is between -1 and 0. When in the interval from -1 to 0, x is negative. So as a result, okay, so we can have the following. We can draw the following conclusion. Okay, if x is between -1 and 0, derivative, the first order derivative is negative. And that means f is decreasing. Okay? If x is larger than 0, the first order derivative is a positive. Is positive. So f is increasing. So we got the interval of increasing, decreasing. Okay, the interval from -1 to 0, right? If you like the interval form, the textbook said use the interval form, right? I.e., i.e. F is decreasing, increasing. But what about 0? We're looking, so we have answered the question of interval decreasing, increasing, and the critical number. Okay, when we set derivative, first order derivative equal to 0, we get a critical number. Right, with the critical number. In this case, the numerator must be 0, right? And then we get x equals 0, or 3x plus 4 equals to 0. But we know that x equals to -4/3 is not even in the domain of the function. So it's not in the domain of the function. Okay, thus not a critical number. Okay, here I'd like to explain to you why. The definition of a critical number, let's take a second look. Okay, the definition of a critical number. So please look at the definition of a critical number. Right, we have that. What is the definition of a critical number? The definition of critical number, let's go down, 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 down. Let's see. Okay, we have the definition of critical number here. The definition of critical number says okay, so I'm going to share the screen with you so you can see it. Share screen. Do you see that? Right. Stop sharing. Share screen. There. Okay, so you see the definition of critical number, which is right here. It says a critical number of a function f is a number c in the domain of the function, such that so not only is in the domain of the function, but also is either the derivative is 0 or derivative doesn't exist. So in either cases, c has to be in the domain of f. Since x is equals to -4/3 is not even in the domain, therefore it's not qualified to be a critical number. Okay, so the only critical number we have here the only critical number we have here is c equal to 0. So when we are looking for local max, local min, this is made very easy because the derivative of the function, which is about 0, right? The derivative of the function to the left of 0 is decreasing, increasing. So that makes, so f, okay, so let's quote first derivative test. Okay, so f derivative, okay, from left to right of 0 changes from negative to positive. Thus, f has a local minimum. And the local minimum, of course, can be found by plug in 0 in the original function, and we know that's 0. So now we found the local maximum and local minimum. We don't have a local maximum. Okay. And the next, of course, we are going to look for concavity and inflection point, for which we have to find second order derivative. In order to find second order derivative, let's see, we have the first order derivative here, and we have, we have all these different forms. Just take this first order derivative, and we're going to take the derivative of it. So first order derivative is here, and we're going to find second order derivative, which is going to be the derivative of the first order derivative. Quotient rule. Okay, so we're going to apply quotient rule. Okay. So the denominator, so what I'd like to do is that I'm going to bring the 2 outside. Okay, so just keep the 2 outside in the denominator. Okay, 2 under 1, right? So I'm taking derivative of this piece. Oops, sorry. I'm taking derivative of the part and bring the 2 outside. I'm taking derivative of that piece. Okay, just make it a little bit simpler, okay? So we have the 1/2 outside, and then we apply quotient rule. So that means we're going to square the denominator. We're going to square the denominator. In this case, let's put the derivative, the denominator in the form of power 3. And write this as, root x plus 1 to the power of 3. And then we're going to square this power 3. Okay, that's going to be power 6. Okay? Because the root of x plus 1 is, so let me put a little note here. I hope you guys are not confused. Okay? The reason we write it this way is because root, this piece is equal to the root, right, squared. And of course, multiply that. That's how we get that root raised to the power 3. We're trying to, maybe we can make it simpler, okay? Now, taking derivative of this piece, so it might be easier, we just write 3x squared plus 4x. So write it 3x squared, 3x squared plus 4x. So that makes it easier to find the derivative, right? So let's write it in this form, just like that. Okay, so that was the 2. Okay, so we're going to use this form to differentiate the first order derivative. Okay, so now we are applying the quotient rule on this piece. We take the 2 outside. This is very algebraic, and there are more than one way to do it. So feel free to try your way. You can even put this on pause and do it whatever way you prefer, and then come back, because the right answer should be the same. Okay. All right. So I'm going to differentiate the top. Okay. So 3x squared being differentiated as 6x plus 4. Multiply the denominator. Right? Subtracting. So now we're going to differentiating the denominator. So put this in parentheses. I'm going to differentiating the denominator, this piece. When we're differentiating this denominator, of course, we're going to use the chain rule. Okay, so that's going to be 3 times root of x plus 1. Well, we first see it as a power, u to the power 3, so 3u squared, right? And then we're going to differentiate the u. The u, differentiating u, that's going to be equals to 1 over 2 times the square root of, never mind this, okay, square root of x plus 1. Okay, and the derivative of x plus 1, of course, is 1. So we got something like that. Okay, you must do it along my side, otherwise it's pretty hard to follow. Okay, let's simplify. So when we try to simplify this, what do? Well, this is multiplied by 1, so we just trim some of those unnecessary piece. But notice you have a root of x plus 1 squared and the root x plus 1 to the power 3. And this is root to the power 6. So this power 2 and this power 3, right? And there's a power 2 here, so they can reduce. So we take this, right? So this will be 4 left. And that will be just 1 left. Okay. And remove that 1. So this time it might be a bit easier. We don't need this parentheses anymore, but we have this complex fraction. If you like, you can put the 3 in front of it. Okay. And the same trick, we're going to multiply 2 times this is a common denominator. We're going to take this and multiply that, principle number 1, multiply that. Common denominator, we multiply it on top and bottom. And now let's see what we get. Right? And these 2 pieces makes 1. Gone. And this piece, we can bring the 2 to the front of it. We can even have the 2 join the half. Okay, we can even have the 4 if you like. And this will be power 5. There. Now, there's a 2 here. So I'm going to put the 2 in the front. You cannot take it out because here you have a subtraction. You cannot take it out. But these 2 pieces, that's going to make x plus 1. Okay. All right. So now what we can do is that there's no common factor here. You cannot cross out anything from the top to bottom. This 2 doesn't go with the 4. Okay, don't do that because you don't have a 2 on this term. So what we can do, we're going to FOIL. Okay, let's FOIL. So let's FOIL this. Okay, so we have a 2 times, so 6x times x, that's a 6x squared. 6x squared times 2, that's 12x squared. Okay, 6x times 1, that's 6x times 2, that's 12x. 4 times x times 2, that's 8x. And 4 times 1 is 4, 4 times 2 is 8. Subtracting, this will be 9x squared. 9x squared, right? Subtracting 12x. All right. Then what do we get? The x squared term and x squared term will combine. So we get 3 times x squared. The negative 12x and 12x, these two will reduce to 0. So we got 3x squared plus 8x plus 8. Can we take the 8 reduce with the 4? No. Okay. And what's on the bottom? What's on the bottom? The bottom is we can put the 4 together to join it. And remember, we take second order derivatives. Finally, we get second order derivative for what? To determine concavity. Determine concavity. So now we found the second order derivative, and let's look at the sign. When it does change sign? The denominator obviously is always a positive, right? Remember, the domain is still x is larger than -1, right? That's our domain. The domain of the function and domain of the derivative and the second order derivative. The denominator is always a positive. How about the numerator? Numerator is a quadratic form. When does it change sign? Okay, so numerator, okay, so let's write down, okay, the denominator is a positive for, for x larger than -1, needless to say, okay, the numerator is a quadratic function, right? So if we set it equal to, if we look at this quadratic function, we set it equal to 0, then we can discover what is the sign, right? So we're going to take this quadratic, if we set it equal to 0, we set second order derivative equal to 0. Denominator cannot be 0, the numerator, if the entire thing is 0, the numerator is 0. So when will the numerator equals to 0? So we're solving this quadratic equation. And we all know about quadratic formula, right? So we're going to use a quadratic formula because it looks like the factoring is going to be, it's going to be a lot of work. Okay. So we're going to look at the quadratic formula. Before we look at the quadratic formula, we like to look at the discriminant. Discriminant is because in the formula, quadratic formula, there's a b squared minus 4ac. Okay, b squared minus 4ac. And in our case, b is 8, right? This is 8 squared minus 4 times a, which is 3, times c, which is 8. What do we have here? We have a 64 subtracting 12 times 8, that's 96. And this is a negative number. This is a negative number. And what that means is there's no real number solution. Or you say we have 2 complex number solutions. And because this is a parabola, this parabola opens up, right? This parabola opens up and it doesn't touch the x-axis. Okay, this parabola opens up. It doesn't touch the x-axis. So imagine that parabola. And if you like, you can graft it. You can even graft it. All right, so to confirm our observation here, so first of all, you can see that the numerator is a parabola that opens up, but it doesn't touch the x-axis because there's no x-intercept, right? That's what basically this says. There's no real number solution. So it's a parabola opens up and never touches the x-axis. So if you can imagine that, and you look at the parabola, right? And make some adjustment, because this, you have to make some adjustment to see that if it's so this is make it 10 and make it -1 for the y's. You can see the parabola is above x-axis. What does that say? This says the numerator is always positive. If the numerator is always positive, denominator is always positive, this tells us that the second order derivative is always positive. For all the x's, for all the real numbers. But of course, we are only concerned for x is larger than -1, which is relevant to us, right? Therefore, the entire curve f is a concave up. Concave up in its domain. Is there any point of inflection? No points of inflection. What you can see here that we know all of the principles. It's the algebraic part, right? That takes a lot of time to work it out. So that's why you need to have a strong, you need to have a strong algebra foundation. Okay, last but not least, and then we are going to sketch, right? And the sketching is we can use the we can use a graphing tool, but with the graphing tool, it only gives us, some part of the picture. Okay, it only gives us some part of the picture. And we are going to apply what we have found, right? First of all, the domain is from -1 to infinity, right? So you're not going to see any picture, to the left of -1. You're not going to see anything on -1. So here I'm going to just make some random adjustment and make changes accordingly. You can see the picture doesn't cross -1. So if I draw a vertical line, which is the vertical asymptote, right? It is not going to touch the curve. I must have made a mistake. Oh, never mind. So the 10 should be outside. Should be inside. Okay. So the vertical asymptote, there's no horizontal asymptote, and 0, 0 is the lowest point, is the local minimum. Local min, right, is a concave up. Concave up entirely. Concave up entirely. There's no point of inflection. You see, this question actually is not super hard, but I think the algebraic part could get us to really spend a lot of time there. So and you can see the basic techniques and algebraic skills are the skills that you already know and familiar with. You just need some practice. All right, so that's the second example, and we have finished. And it requires some knowledge about quadratic functions, right? So the next example, I think I'm going to make another lesson, okay, because I don't want to make this too long. But anyway, thank you for watching. Until next time, thank you for watching.